Hello and welcome to another lecture from my class, PSYC 440/640. The class is called Experimental Methods, but it's really more of a class on univariate data analytic techniques from a model comparisons perspective. As always, or at least as usual, I think, I'm beginning with a webcomic, this one from phdcomics.com. I think the humor is there and doesn't need too much explanation, at least if you spent any amount of time around academics and had them describe to you or represent for you with figures and pictures their theories. Sometimes things can be a little too complicated, I suppose. Anyway, the goal of today's lecture is just to give us a little bit more practice using multiple regression and playing around a little bit with mediation and moderation, two topics that we've obviously spent a fair bit of time on this unit. So it's really going to be a bit of a review and a little bit of practice. Here's the review part. Now, where we left off last time, we were talking about moderation and mediation, two terms which mean different things, although they're sometimes incorrectly substituted for one another. In the case of moderation, we're talking about interaction. That is, the finding that the effect of one predictor variable on the outcome variable varies or changes across different levels of another predictor variable, which we call the moderator or the moderating variable. In the case of mediation, we're making a more subtle claim, or we're testing a more, perhaps more interesting effect, whereby the effect of a predictor variable on an outcome variable occurs through or via a pathway within another predictor variable, which we're calling a mediator. So the example I used last time was based loosely on my understanding of eating disorder research, and the gist of it was negative body image is related to eating disorder symptoms, but some amount of that relationship occurs through or occurs via changes in self-esteem. So to the extent that someone has a higher negative body image, they dislike their body shape or size more, that leads them to have lower self-esteem, and that's what leads them to have higher eating disorder symptoms. Now, I don't make any claims as to that being actually true. That's just kind of the scenario I set up when I created some fake data to illustrate this example. And here's some output from an analysis that we conducted using process, and you can see some of the kind of highlights here. We first looked to see whether the effect of the looked at the effect of the predictor variable on the outcome variable when the mediator was not in the model. You can see that up at the top, and then we can see the effect of the predictor on the outcome variable when the mediator is in the model. That's a little bit further down there. And you can see that there is a difference between those unstandardized regression coefficients, suggesting that at least some of the story, if you will, might occur because of that mediating variable. That mediating variable in this case is self-esteem, and you can see that highlighted there, that indirect effect. Now, there are different ways of estimating the effect size of that indirect effect, how big it is, and it's notable in this example that all of these different estimates of effect size have confidence intervals which are arrived at through a bootstrapping method. These confidence intervals all overlap with 0, suggesting that the effect size of this indirect effect occurring through self-esteem, may not be significantly different from 0. And so in a sense, what we found with this analysis, again, it's a contrived example with fake data that I just made up on my computer, is that the indirect effect of negative body image on self-esteem, on eating disorder symptoms via self-esteem is insignificant and is rather small. And this probably is no surprise, or it wasn't really a big surprise to us when we did the analyses, because it just was the case that self-esteem wasn't itself very highly correlated or very highly related to negative body image. So there wasn't much of a link there between our supposed predictor variable and our supposed mediator variable. And without that link, then of course the mediator can't be a good mediator because it's not really linked or connected to the main predictor variable. So that's just a bit of a review. Hopefully that makes sense, and it's of course what I covered last time. It's worth noting, although I don't think I have an extra slide for it right now, but it's worth noting that in these examples, we gathered data on negative body image, self-esteem, and eating disorder symptoms all at the same time, presumably with some questionnaires that we administered to a group of participants in our lab or in our clinic or whatever. And so the idea that one variable necessarily is the predictor and another is necessarily the outcome and the third is necessarily the mediator is not fixed. I mean, you could imagine shuffling these variables around, and if you did that enough and if you fiddled enough with the parameter inputs on process, you may in fact find something that looks like a significant indirect effect or a significant evidence of mediation. Now, perhaps that's acceptable for exploratory data analysis or for hypothesis and sort of theory generation. But as I mentioned last time, and as I'll mention later in this lecture, I think I want to caution you against just fiddling around with statistical software, especially something like process, because it can be abused so as to give you what look like significant results, but which may not be very robust. That is, they may not replicate in further work. So something to keep in mind. And keeping that in mind, let's go through and just do a different example that will give us opportunities to practice some of the stuff we've learned across this whole unit. So again, let's try and work through an example. And if you're enrolled in my class, you have access to some notes on Blackboard. As I encouraged you in actual class the other day, try not to look at your notes when you go through this example. See how much of this stuff you can do on your own. Test yourself. Okay, so the basic setup is, imagine you're a school psychologist and you're studying achievement. That is, studying like essentially grades, how well people do on standardized measures of knowledge acquired. You're doing a non-experimental study where you have some predictor variables. You've got ability, that's scores on standardized tests of intellectual kind of intellectual horsepower, if you will. I'm sort of struggling for a metaphor there. IQ, intelligence, would be a more common term that we might use to refer to intellectual ability. So intelligence or ability is one predictor. Television viewing, how many hours a day you watch TV, is another predictor variable. And socioeconomic status is a third one. And of course, our outcome variable, kind of like I said before, is some sort of measure or compositive measures of various achievement tests. Now, if you're enrolled in my class, you have access to this data set. It's called Student Achievement. If you're not enrolled in my class, I'm afraid you're out of luck, because this is a pretty big data set and there's no easy way that I could kind of make a slide of it. So you'll have to kind of just follow along, but maybe not have the opportunity to play along. And I apologize for that. Let's imagine our research hypothesis is something like ability, that is intelligence, IQ, whatever, moderates the relationship between television watching and achievement. There's some relationship between how much television you watch and how well you do in terms of your grades at school, but that relationship is moderated in some way by your intelligence. And for the time being, let's just assume we have a good theoretical basis or empirical basis to make this hypothesis. Maybe there's some theory that suggests that intelligence, buffers the effect, the deleterious effect of television watching on intellectual performance in school, or maybe as teachers we've just observed, kind of clinically or in the classroom, that students who watch a lot of TV do worse in terms of their grades, but maybe the smarter kids, it's not such a big deal, or maybe the smarter kids are more harmed by watching a ton of TV. Who knows? Assume that we have some good reason and we're not just totally making up this hypothesis, when in fact I am totally making up this hypothesis. If this was a real example, or if this was real research that you were doing, I would encourage you to kind of sketch a diagram for your analyses. I like to do this almost anyway, almost always, just to kind of help me clarify my thinking. And in this case, our predictor variables, ability and television, are arranged thus. As you can see here, ability we're treating as a moderator. Television watching we're treating as our main predictor variable, and as I noted before, achievements are our outcome variable. By the way, I'm not using SES in any of these examples. I started to include SES in some of my analyses, but it just got too complicated, and this lecture is already getting long enough, so I've kind of dropped that variable entirely, in case you're wondering. And once again, let's assume that we have some good theory-driven or kind of empirical observation driven reason for testing a moderation effect that looks like this. And let's also hope that we have some fairly specific prediction about the nature of what this moderation effect looks like, whether ability score buffers or enhances the effect of television watching on achievement, or so on. Now, by this point in the unit, you're probably pretty familiar or pretty comfortable, I hope, with the idea of testing a moderation or testing an interaction effect. You basically can do it through a multiple regression in which in step 1 you enter the main predictor variables, and in step 2 you enter the interaction term to see whether including that interaction term or allowing that interaction to exist in the model improves the fit to the data. Now, in terms of the options for analyses, you have a lot of them in SPSS, of course. One of the ones you really want to focus on are the effect size. R-squared's an easy choice there for effect size, and particularly the change in effect size when you include the interaction term in the model. That's part of the rationale, or part of the reason for doing this analysis hierarchically. That is, doing first the main predictor variables and then the interaction term to see if that interaction term improves the fit of the model. We also want to get things like regression coefficients, probably with some confidence intervals, because we'd like to eventually express the model for simple effects and do some simple slopes analyses. We also probably have a lot of different options for graphing and examining residuals, etc., etc., etc. Which kind of brings me to an important point. We sometimes rush into our analyses, like if you're excited to get to your analyses in your laboratory, or in my examples in class, I'll sometimes kind of barrel ahead to kind of get to the point that I'm trying to lecture on. But for the purpose of this lecture, let's consider some important points that probably we should think about every time we do analyses. So one of these is, should we center our predictor variables? Now, there are some reasons we often like to center predictor variables. We don't always have to, but we often want to. And one of these are situations in which the predictor variable doesn't have a natural zero value. So we have two predictor variables, or a predictor and a moderator. Essentially, they're both really predictor variables. And that predictor variable, or that moderator variable ability, doesn't really have a natural zero. If we are thinking of ability as like intelligence or IQ, there really is no such thing as someone with zero IQ or zero intelligence, all joking aside. So centering the predictor variable, or at least that predictor variable, centering that moderator, might help us interpret the intercept of any model that we make with it, because then the intercept is reflecting a prediction for people who are at the average level of ability, or the average level of intelligence. Now, television watching does have a natural zero. It is possible, it's even likely that there are people out there in the world who watch zero television. Although I guess you could imagine that if you're thinking about school children or school-aged, young people, it's probably pretty rare to find people who watch absolutely no TV. So even there, you might say, gosh, a zero is not particularly interesting to us. An average or a mean level is more interesting. Now, the other reason we the other reason why we sometimes like to center predictor variables is that we might want to test an interaction term. Now, at this point, of course, we've already committed to that. So, it's not a question of we might want to do this. And centering the predictor variable usually makes testing interactions a little bit easier, because it reduces potential problems with multicollinearity between the predictor variables and the interaction term that is made from them. My little asterisk here is just to suggest that, again, we should have plans for our analyses before we start doing them. We shouldn't be like, well, gee, we might test an interaction. Let's just go ahead and center predictor variables. In this case, it's good to think ahead. So based on that, let's just go ahead and center both of the predictor variables, and then of course create an interaction term for them. Now note here, we don't need to center the interaction term itself. We just center the predictor variables, one or both of them, in this case both of them, and then multiply them together to create that interaction term. So one thing we should think about before we really get into our analyses is, do we want to center predictor variables? Answer, at least tentatively, is yes, we do. We should also consider evaluating, or we should consider evaluating different sources of bias. And those can include things like outliers, influential cases, and violations of the assumptions that go along with linear models. Now, again, in some of my examples in class, I've just kind of barreled ahead and ignored these concerns. And maybe in my own experience, if I'm perfectly honest, there are times where in the lab or doing data analysis, I've just kind of barreled ahead without thinking about these things. But I would encourage you, and here's some practice, to really think about the things that can make our model, our augmented model that includes our predictor variables, includes our interaction term, can make it biased with respect to predicting the outcome variable. And here are some of the sources of bias. And they're sources that we can think about. So first, let's consider outliers and influence. Looking for outliers isn't really very hard to do. The only trick or kind of important thing to remember here is that when we say outliers, we're really talking about outliers with respect to the residuals that the model makes. So we can look for, or we can have SPSS do some case-wise diagnostics where it identifies cases with large standardized values for residuals. We can also have SPSS save into the data file values for standardized residuals, or for that matter for unstandardized residuals, and we can just visually inspect the data to look for large values. And remember, it's certainly possible, it's even likely that there will be some cases with large values for standardized residuals. We just don't want to see a lot of them, because if we see a lot of them, or if we see a lot of them piling up on one end, like a lot of high values for residuals on the negative side or high values on the positive side, that starts to suggest to us that our model may be biased in terms of prediction. It may be kind of overshooting or consistently undershooting. Or if there are just lots and lots of extreme values, it may be just a generally poor model. Influence is a little bit more challenging because it's a more complicated topic to think about. But if we're looking for influential cases, we can think about influence in some different ways. One is we can look for evidence of influence on the model's prediction of particular cases. So there are various regression diagnostics that we can use that will tell us whether the model does a kind of a bad job predicting an individual case. So for instance, we can look at studentized deleted residuals. And you may recall that these are standardized, or technically studentized, differences between the adjusted predicted value and the original observed value for each case. So we'll get studentized deleted residuals for each of the cases in our data set. And essentially what they're telling us is how badly does the model, they're giving us a sense of how badly the model predicts a case when the case isn't in the model. So if a particular case, whether it's in or out the model predicts it about as well as either way, then that case isn't particularly influential. If there's a huge shift where the model predicts a case really poorly when it's not in the model and better when it is in the model, that means that case has some influence, at least influence with respect to the model's prediction of it. Another way to look at this idea is to look at standardized DF fits. These are standardized differences between adjusted predicted values and original predicted values. So they're similar to studentized deleted residuals. But what they're giving us is a little bit more of a sense of how well does that case influence the model's ability to predict it. We can also consider influence in terms of the model's ability to predict other cases, or how much an individual case influences the model's ability to predict all the other cases in the data set. And here we have calculations like Cook's distance and leverage, which are sort of indicating to us the influence of the single case on the model itself, how much that one case influences how well the model predicts all the other cases in the data set. Along the same lines, we can look at standardized DF betas. These are just standardized differences in the regression coefficients for the model when all the cases are used and when one case, each particular case is excluded. So again, you can imagine if pulling out a particular case caused those regression coefficients to really change a lot, then there's something about that case which is really influencing how well the model is predicting all the other cases in the data set. So, another source of information. I think what's sometimes hard about regression diagnostics is there are a lot of different kinds of them, and they give us similar sorts of information, or they give us information that is similar but maybe slightly different, and it can be hard to kind of keep them all straight in your head. I like to divide the regression diagnostics, at least the ones for influence, into those which are more concerned with how an individual case influences the model's ability to predict it, and the others which are concern the model's ability, the influence of a particular case on the model's ability to predict all the other cases. And then when I actually run my analyses, I try and consider multiple sources of information to see if there's a general pattern emerging to suggest that a given case has a lot of influence or maybe doesn't have so much influence. Okay, well, if all that isn't too much to take, let's move on and think about some other potential sources of bias. And these are violations of assumptions that we need to make for our analyses. And there are some assumptions which are pretty basic. For instance, one of our assumptions is the assumption of linearity. That means we're assuming there is a straight, that is not curved, line relationship between the various variables in our model. That's not something we can really check. That's just something we sort of assume. We assume that the relationship between, for instance, television watching and achievement it can be described by a rectilinear line. It's not the case that there's a curvilinear relationship between those two variables. Or we assume that the moderating effect of ability occurs in a rectilinear fashion, a straight line fashion, either more or less moderation. It's not curvilinear in its relationship. Now, there are out there in the big world of statistics ways of doing curvilinear modeling, but they're a little bit beyond the scope of this class. And frankly, the way I'm feeling today, a little tired, a little worn out, they're beyond my ability to think too carefully about. So suffice it to say, one of the things we're assuming is just that there is a linear relationship there are linear relationships between our variables. And the important point here is you should have some theoretical position on this. You should have, based on your understanding of the variables you're studying, you should be able to say, yeah, that's a reasonable assumption to make, or gosh, no, that isn't. If you're in the gosh, no, that isn't position, then maybe you should revise your plan or use different statistics. Another assumption that we make is the assumption of independence. Here we're assuming that scores on the outcome variable for individual cases are unrelated to each other. We've talked a little bit about this in the previous unit, so I won't get into this too much more, but I will note that this is another one of those assumptions that we don't really test so much as we kind of think about. We think about the nature of our research design and our research methods. We ask ourselves, to what extent is it possible that an individual participant's score might influence another individual participant's score or be associated with another individual participant's score? If the answer is, well, there's not much influence or not much effect there or not much chance of that, then we're maybe fairly comfortable making the assumption of independence. If we start to worry that maybe the participants' scores are influencing each other, then maybe we can't make this assumption and we have to use, again, different statistics. Finally, an assumption that we make that we can actually test a little bit is we're assuming not perfect multicollinearity. That is, we assume that our various variables in our design and in our analyses can be correlated with each other a little, but we're assuming that they are not all perfectly correlated. And this is a good assumption because it's one that we can test. And although I don't think I do it in my lecture today, you could very easily make a correlation matrix to look at the correlations between the variables in your analyses. And also you can note that by including an interaction term which is based on centered predictor variables, or a centered predictor variable and a centered moderator, we're kind of reducing problems with high levels of correlation between those terms. So some assumptions we just have to make and kind of think about. and I guess in the case of not perfect multicilinearity, we can check a little bit. Other assumptions we can actually check, and we really should check. One of these is normality. And here again, we're talking not just about the raw data itself, we're talking about the distribution of the residuals. Is that distribution normal in shape or not? And we can test that in various ways, graphically or with statistical tests. We're also making the assumption of homogeneity of variance of residuals, meaning the variance of the residuals is consistent across different levels of prediction. And that's something we can also test, and in fact we should test. Now this is all a lot to think about, but it's important. Should we consider and evaluate sources of bias? Of course we should. This is the general order that I approach things. I usually look for the outliers first, then I start to think about influential cases, and then I round out thinking about assumptions. The rationale or the reason behind this ordering is that often if you can deal with outliers, if they're present, it attenuates problems with influence and also with problems of violated assumptions, at least some violated assumptions, like the distribution, normal distribution of residuals. You don't have to follow this path, but I think it's a good place to start and a good way to work. First, let's focus on outliers and ask, are there any cases with large absolute values for their standardized residuals? And we're not worried if there are one or two cases, probably, especially in such a large data set. We have 500 people, I think, in this one. But if we saw more than about 5% of our cases with large values, absolute values for standardized residuals, greater than 2, for instance, or if we really saw any with extreme values, greater than 3, that should at least arouse our attention. Also, if we saw a weird sort of shift or skew such that there were large values in the negative direction but not in the positive direction or vice versa, that would concern us a little bit. Now, it happens to be the case in this data set. There's one case who has a large value for his or her standardized residual. So that person is, by the definition we're using, an outlier. Although the simple fact that there's just one person in this data set, or maybe one or two, I mean, big data set, it took me a while to look through it, doesn't really worry us too much. It doesn't seem to be the case that there's a very large number with extreme values or even with fairly large values. Next, let's focus on influential cases. And here we can think about influence different ways. First, let's think about it in terms of the model's ability to predict individual cases. And we can ask, are there any cases with studentized deleted residuals that have extreme values? They're greater than 3. And again, our case 491 happens to have a large value for his or her studentized deleted residual, suggesting that there's a large studentized, that is, difference between the value that the model predicts for this case when it is not in the model and the actual value for the case. This suggests that the model does a poor job in predicting this case when the data isn't in the model. This model has a lot of influence on the model's ability to predict it. And we can also focus on the model's ability to predict those particular cases by looking at large values or extreme values for DF fits. And it's worth noting here that case number 491 doesn't have a particularly large value for his or her DF fits, suggesting or showing that there isn't a large standardized difference between the value that the model predicts for this case when it's not in the model and the value that it predicts when it is in the model, suggesting the case doesn't have a lot of, or that this case doesn't have a lot of influence on the model's ability to predict it. Next, we can focus on influence in terms of the model's ability to predict other cases. We can look for cases that have large values for cooks or leverage. Here, our person ID number 491 doesn't have particularly large influence in terms of his or her cook's distance or leverage value, nor do any other cases, suggesting that this case, 491, doesn't influence disproportionately the model's ability to predict all the other cases. And we can look at that same issue by examining DF betas for all of the cases, and again look for large or extreme values of standardized DF betas. And case number 491, or I should say ID number 491, doesn't have large values for DF betas, nor do any of the other cases, suggesting that the standardized coefficients of the model don't change very much as a function of whether or not case number 491 is in the data, or is in the data set that the model is made from. So this is just another way to think about influence from the perspective of the case's influence on the construction of the model and the model's ability to predict all the other cases in the data set. So if we put it all together, it looks like there are a few, or maybe there's a few, or even just like one or two outlying cases with respect to residuals, and really no very influential cases. Hopefully you could follow along with what I just went through. The basic gist is I first looked for outliers, and then I looked for influence, recognizing that often, although not always, it's the case that outlying cases are influential cases. In this particular example, ID number 491 was an outlier in terms of his or her residual and had some evidence of being an influential case, but not a lot of evidence, or not when we considered the idea of influence from different angles or different perspectives. And the simple fact that there's one case in the data set like this shouldn't really worry us. Also, the fact that this case isn't particularly influential, it's hard for individual cases to be very influential in large data sets. There's a lot of other data, in a sense, competing against them. Problems of outliers and influence are always a lot worse in small data sets. So, yet another reason to tend to prefer large data sets over small data sets when doing analyses. Now you might be asking, well, what would we have done if we had found a lot of outliers or a lot of influential cases? How would we have dealt with them? Well, we could have removed those cases if we found particularly influential cases or particularly outlying cases. We could have Windsorized the cases, that is, brought them into the fence. That we could have found cases that were outliers and then taken the values of those cases on the dependent variable or the outcome variable and reduced them, or brought them closer to the mean for the overall sample, so brought them to the fence, as it were. Or we could have even transformed the entire data set. If our data set was very skewed and we saw a lot of that skew showing up in our residuals, we might have log transformed or square root transformed the data set. I tend to not like to do this because it puts the data into what's often a kind of a non-obvious metric, because we're talking about, instead of an outcome variable in its natural metric, we're now talking about it in its square rooted metric or its log transformed metric. But this is sometimes done in some types of data, not much in the examples that I've given in this class. Although, by the way, I do think I have a supplemental video where I talk about some of these techniques for dealing with unusual data sets or problems with violations of assumptions. Speaking of violations of assumptions, let's focus on some of those violations of assumptions. Well, I talked about the assumption of linearity, and I made the point already that this is just a basic assumption of the type of model building and model comparing that we're doing. We're not working with curvilinear models. So there's no real way to evaluate this assumption. We just have to think a little bit about the theories that we have for the particular variables that we're studying, and ask, is it the case that we can assume straight line relationships between them? We can think about the assumption of independence. Again, this is a matter of kind of our design and our methods of our study. Hopefully we've designed our study, hopefully we've gathered data in such ways to minimize problems with non-independence. And then another assumption we have to make is the assumption of not perfect multicollinearity, or not perfect correlation between all of our variables. This is something that we can check on, and happily centering predictor variables is going to help decrease the one problem that we sometimes have with multicollinearity, which is multicollinearity between predictor variables and interaction terms that are made from them. So we've already kind of dealt with this a little bit. Other assumptions that we can deal with include the assumption of normality, and here we're talking about normality with respect to the residuals. You can get SPSS to produce for you in any of a number of different places the distribution of those residuals. You can see here that they are rather normal in shape, either just looking at a simple histogram or a QQ plot, which is essentially the same thing as a PP plot. I can also run I can run two formal tests of normality, the Kolmogorov-Smirnov and the Shapiro-Wilks test. You can see that both of them are not significant, which is suggesting that the distribution for residuals is not significantly different from a normal distribution. So looks like the distributions of residuals are normal. I can also think about the assumption of homogeneity of variance, again, with respect to residuals. Here, there are different ways to evaluate this assumption. The easiest ones to use for regression type analyses are just simple scatter plots, where we, for instance, look at different levels of the predictor variable, in this case television viewing, and the distribution of standardized residuals. We can kind of get a similar idea if we look at different levels of prediction, like at different levels of the predicted outcome variable. And again, standardized residuals. What we want to see here is roughly the same spread of residuals, the same sort of height, if you will, of those dots at different levels of our predictor variable, or at different predicted levels of the outcome variable. Here, both of these scatter plots look a little bit ovoid in shape, but there's not a weird sort of delta, sort of a triangular shape, such that the cloud is very narrow on one end and very wide on the other. That would be concerning, because it would suggest that the level of error, the distribution, or the sort of the margin for the residuals, gets much bigger at some levels of prediction than it does at others, or at some levels of our predictor variable than it does at others. We don't see a ton of evidence for that here, which is good, because it suggests that we can maintain or retain our assumption that the variance of the residuals is homogeneous, or roughly homogeneous. So if we put this all together, in terms of the assumptions, it looks like there are no problems with violated assumptions. The only reason I put the little parenthetical question mark there is some of these, for instance, the assumption of linearity, the assumption of independence, are things which we can't formally test or evaluate very closely. We have to more or less think about them, and we can probably never be entirely satisfied with the conclusions of those thoughts. Anyway, with all that said, now we can move along and look at our actual results, which is the part that we're probably really hoping for, or really interested in. We can ask the question, so does the interaction term improve the model? That is the model with the interaction term statistically significant? Is that augmented model a better fit for the data than the compact model that has no predictor variables in it? And maybe more importantly, does the addition of that that interaction improve the fit of the model? Is there an incremental improvement in fit when we go from just the main predictor variables to those main predictor variables and the interaction term? And I haven't really included any SPSS output here, but if you've done these analyses, you know that the augmented model that includes the predictor variables, that is the predictor variable and the moderator and the interaction term, is statistically significant. It explains or is associated with about 53% of variance in the outcome variable, and is significantly better fit to the data than is an augmented model that includes just the predictor variables but not their interaction. And I forget exactly how much of an improvement there is. It's not a big improvement. I think it's like 9% of variance, but not bad. So we found an interaction that is significant, suggesting there is a moderated effect here. What we'd like to do is characterize the nature of that moderation. One of the first things we might want to do is make one of these kind of quick and dirty graphs for the interaction. And in order to do this, I kind of somewhat arbitrarily made ability groups. I took ability, our moderator variable, which is naturally continuous, and I formed groups on it, which again is, or I shouldn't say again, but as I have noted in previous lectures, is something you probably ought not to do, or at least it ought not to be your only step in your analyses, because it can create some problems, but it's often a first step. It's a nice quick and dirty step. Doing that, I was able to make the following graph in SPSS, and you can see here the relationship between television viewing and achievement for people in either a low ability, a moderate or medium ability level, or a high ability level. And you get the kind of impression that there is a negative relationship between television viewing and achievement for people who are of high ability, high IQ, but maybe a more positive relationship or a not quite so negative relationship among people with moderate or medium or even with low ability. So the quick and dirty graphing approach is often a good first step, but we'd like to get a little bit more precise than that. And one way we can do that is we can express the model for the interaction. We can write out the model, that is, write out the regression equation in such a way as to show how it changes at different levels of our moderator variable. So we're just rearranging the terms here, and we now have a term to refer to the intercept and the slope of the model, each of which contain the moderating variable ability. Again, we sometimes call this the simple relationship between the predictor and the outcome variable. Simple's in those little quotes because really it's not a simple relationship. It's a relationship which has an intercept and slope, and those intercept and slope change across different levels of ability. And you can see some interpretation of the values written there below. So expressing the model this way is helpful because it suggests to us that as people have greater levels of ability, that is greater intelligence, the intercept for the model rises somewhat. As they have greater levels of ability, though, the slope for the model becomes more steeply negative. It becomes more stronger and steeper in the negative direction. And if we want to actually create a more precise graph to illustrate this, what we can do, of course, is we can predict scores on the outcome variable for people who are at one standard deviation below the mean of the moderator, at the average level, the mean of the moderator, and at the high one standard deviation above the mean, which is very easy to do. All we need to do, because our moderator variable is centered, the mean is of course going to be 0. All we need to do is get the value for the standard deviation, which you can see right here from some simple descriptive statistics. And then we plug that value in to the model for the interaction. So we take our model here and we plug in the value for one standard deviation below the mean and solve, and that's our model that's what the how the model looks when ability is one standard deviation below the mean. We do the same thing plugging in 0, and now we have the model for when ability is at the mean. And finally, we plug in a value for one standard deviation above the mean. We get the model for when ability is at one standard deviation above the mean. If we put all this information together, we can make a little table, which I think pretty easily would represent to our reader what's going on. And we can even use that information to make some graphs of those simple slopes. And they look a little bit like this. Not all that different from what we saw using the quick and dirty approach, but slightly different. You know, those intercepts are a little bit different. Those slopes are probably, they're not very different, but they're slightly different. And that reflects the actual greater precision of using this approach rather than the previous approach. So our significant interaction, or the significant improvement of fit in the model when we include the interaction, tells us that ability moderates the relationship between television and achievement, and it sort of looks like TV is a predictor or is predictive of lower achievement, maybe at average levels of ability and at high levels of ability, but it's predictive of higher levels of achievement at lower levels of this variable. So it's kind of an odd finding, and one that probably goes down to the fact that this is fake data that I made up. But that's the kind of the nature or the picture, literally, of what the moderating effect looks like. Now, we might want to be a little bit more fine-grained in our analysis. That is, we might want to find specifically at what levels does ability cause the effect, or is ability associated with the effect of television on achievement shifting from positive to negative. And we could find that by hand, or we could go the long way by just substituting in different values for ability, and finding, plotting many lines. Or if we were lazy, or at least as I often am, we could use process, which will do a lot of that work for us. So running through process, which I haven't bothered to show you all the steps because you can look at my previous lecture to see that, I could take a look at this table for the Johnson-Neyman technique, and I can see that when ability is below the mean, when the value for centered ability is below the mean, television I'm sorry, the effect of television on achievement is positive. The values for those effects are all positive, as you can see, and they're all significant, as you can see. Now, around the time, or around the level of where ability is at the mean, television is not predictive of achievement. Here, note that the values for the effect are close to 0, and the significance levels are kind of right marginally at 0.05, and the confidence intervals for these effects overlap with 0. So you might say right around the level of ability being at its mean, it's questionable whether there's much of a relationship between television watching and achievement. And then when ability is above the mean, television watching is predictive of lower achievements. You can see here that all those unstandardized regression coefficients are negative in the column for effect. You can also see that those effects are all significant if you look in the column for the p-value, and you can even look at those confidence intervals, and they're mostly not, well, they're all not overlapping with 0. So you get more of a sense of how the relationship between television watching and achievement changes across different levels of ability. A little bit more of a fine-grained analysis. You can see here kind of right at where sort of the threshold for the ability, or for the effect, shifting from negative over to where it becomes more of a positive effect. So again, it looks like TV watching is predictive of lower achievement among people at higher levels of ability, but it is predictive of higher achievement among people at lower levels of ability. By the way, does that really make a lot of sense? Maybe not. I'm sure we could come up with some sort of post hoc explanation for this, but let's keep in mind this is just fake made up data that I used for this example, so probably not worth worrying too much about. We're just trying to do this for practice, and with that in mind, what if we wanted to test some sort of mediation analysis? Maybe TV influences achievement because of ability, or somehow through ability, and thus ability acts as a mediator. It's a little bit hard to understand how this mediation relationship would work, but again, this is just for practice. And remember, we should really have a good theory-driven reason for predicting this or any other mediative relationship. But for the purpose of this example, let's just assume that we do. And recall that what we really want to do when testing mediation analysis, or when running a mediation analysis, is first establish that there's some relationship between television and achievement. That would be C, the little c. Then establish that there's a relationship between television and ability, our mediator, that's A. There's some relationship between ability and achievement, that's B, and then establish that if we have a model that includes both the mediator and the predictor variable, that the relationship between the predictor variable and the outcome variable is less than that in a model where there is no mediator. So make sure, or look to see whether C prime is less than C. That's kind of the gist of the classic Barron and Kenny approach to doing this type of analysis. So again, if you want me to explain it again, we've got model number 1 where we're just looking to find the value of C, model number 2 where we're looking to find the value of A, model number 3 where we're looking to find the model of B, or the value of B, and finally model number 3 where we're including our predictor variable and our mediator and seeing whether that value of C prime is less than the value of C. So we found that television is predictive of achievement. That's good. We found that television is predictive of ability. Well, that's helpful if ability is going to be a mediator. We found that ability is predictive of achievement. Well, that's good because again, it completes the connection. And we also found that TV is less predictive of achievement when ability is in the model. So we have some general sense that there's mediation going along. And because C prime is less than C, it's not absolutely zero, we might call this a partial mediation situation. We haven't entirely removed the effect of or the relationship between our predictor and our outcome by including the mediator. We've only diminished that direct effect. So we want to talk about this in a little bit more of a fine-grained way. We want to estimate that indirect effect, find out how much of the effect of TV on achievement goes through, so to speak, ability, and for that we really need process again. Here's some output from process, and you can see here the effect of the predictor when the mediator is not in the model, the effect when it is in the model, and the difference, which is of course the indirect effect, the effect of the predictor on the outcome via the mediator. And we can see different estimates of the effect size, none of which overlap with zero, suggesting that there is some significant partial mediation for television watching on ability via on achievement via ability. And if we really scrutinized all the regression coefficients, we might find that television watching is associated with lower ability. They're negatively related to each other. The more TV you watch, the lower your ability, and ability is related to achievement, such that the higher your ability, the higher your achievement. So if we put this all together, we might say ability increases achievement, but TV decreases ability. Note that this indirect effect is negative, and we can see that by multiplying the signs of the two steps in the relationship. Television watching decreases achievement because it decreases ability. By the way, this doesn't make a lot of sense. Does it make a lot of sense? Not really. I mean, ability, that is intelligence, should be a pretty stable trait. It's hard to imagine a situation where TV would really change it, unless I suppose maybe like people watch a lot of TV, they stay up late at night and get really tired, and then they don't do well on tests of ability. And see, here I am now kind of making up a post hoc explanation for a strange finding. Why did we find evidence for mediation in our analyses? Well, we had a really huge sample. Well, if not huge, at least really big. There were 500 people, so we had lots of power, and even relatively small effects, such as small apparent indirect effects, can be statistically significant when you have that much power. It's interesting to note, and in fact I think I might have mentioned this in my last lecture, that you sometimes see process criticized in the literature, or more recently even in the social media. Here's a thread on a Facebook group that I follow that's mostly the membership is mostly people who are really interested in research methods and statistics, and here you can see someone asking for advice about how to use process. And you can see if you read the full thread, you can see that process is kind of criticized for making it too easy to find apparent moderation and mediation effects. Some of the responses here emphasize the importance of demonstrating a significant interaction for testing moderation before you wade into using process. And then the other response here emphasizes the importance of using theory-driven hypothesizing, not just sort of fiddling around with process. It's not my purpose here to criticize this particular tool. Rather, it's just to note that mediation analysis, or for that matter, moderation analysis, it's just a tool, and process makes it a very easy tool to use, but it can lead to mistaken or even confusing results. It's also worth noting, as I did in the last class, that there are other ways to think about the whole idea of mediation. People who do a lot of experimental manipulation will often champion that as the better way to really demonstrate mediation, although of course that's not always possible for certain types of things we study. Like if you really thought that ability was a mediating variable, it's hard to imagine how you could manipulate ability, make some people smarter, make some people less smart. There are probably times when we have to use statistical tools like process and similar kind of applications in SPSS or other stats programs. The basic point, though, and I've made this again and again, but it's worth repeating, is that you should always have good theory-driven, empirically driven hypotheses and use whatever your statistical tools are to test those, not just to fish around for significant results, because the more you fish around, the more you're eventually likely to find something, especially if you have a lot of data in your data set and a fair bit of statistical power. So just to finish up, let's talk briefly about how you might report mediation analyses. Assuming that you'd predicted this effect and you'd found it, you might say something like, the effect of television viewing on achievement was partially mediated by ability. The mediation effect size was such and such and such. You could report a table describing the total direct and indirect effects to give your reader a sense of the relative amount or size of the indirect effect versus the direct effect, and so on. Anyway, I hope this has been helpful to you. I'm trying not to make this too long a lecture, though I can see I'm closing in here on about an hour, which is, I guess, kind of typical for me. If you've followed along, especially if you're in my class, of course, you know that your exam is coming up, and I hope that this has been a useful review for you. If you're struggling, be sure to ask questions. If you're not enrolled in my class and want to ask questions, you can just post them on YouTube. I try to find those and answer them as quick as I can. Good luck for those of you who are taking the exam. Good luck for those of you who are just trying to learn statistics. It's a challenging, but I think ultimately rewarding process. So take care, and I'll be back soon with another lecture. Bye-bye.